The last topic we're going to cover in this unit is the relationship between carbon dioxide and global climate. Ecologists talk about nutrient cycles, the way that nutrients such as nitrogen and phosphorus and carbon cycle within an ecosystem within the globe. The carbon cycle describes how atoms of carbon, molecules that contain carbon, cycle back and forth between organic and inorganic forms. The processes we have been learning about in this unit, photosynthesis and cell respiration, play major roles in the carbon cycle. Here's a figure I borrowed from an ecology textbook showing how carbon dioxide concentrations in the atmosphere of Earth have changed over geological time. Check this out. 450 million years ago, the atmosphere contained 20 times more carbon dioxide than is present today. The atmosphere of Earth, the climate of Earth at that time would have been unrecognizable and, quite frankly, uninhabitable to us. So look at what's happening in the next 100 and 150 million years that follows this peak. Carbon dioxide concentrations plummeted to near where they are today. What happened there was the evolution of plants. Plants, as we know them today, terrestrial, photosynthetic, macroscopic creatures, began pulling carbon dioxide out of the atmosphere, fixing it, making it organic, and as forests grew, carbon dioxide levels continued to decrease. As you might know, Illinois has a lot of coal under the ground, and that coal was formed during this time period about 300 million years ago when forests were spreading across North America. Carbon was being fixed. The organic bodies of these plants piled up and were fossilized to create the coal reservoirs that we have today. Some of that drop in carbon level in the atmosphere is also linked to the formation of limestone rock. So if you drive along Route 3, along Bluff Road, and see the bluffs along the Mississippi, those carbonate rocks were created through microscopic organisms taking carbon dioxide out of the water and using it to create the carbonate shells. A key concept in understanding the carbon cycle is the effects that increasing CO2 levels in the atmosphere can have on global climate. You've probably heard of the greenhouse effect. The greenhouse effect describes how carbon dioxide and other greenhouse gases like methane can trap heat energy in the atmosphere, much as the panes of glass on a greenhouse help trap the heat energy. So our figure here shows a simplified version of the greenhouse effect. The gases in the atmosphere, not visible on this figure but implied, are acting to contain some of the heat that would otherwise radiate back out into space. So the higher the concentrations of CO2 in the atmosphere, the more of this radiant heat that will be trapped. Climate scientists have demonstrated a pretty conclusive link between CO2 levels and temperature levels globally. Here's some data from a CO2 monitoring station on top of a mountain in Hawaii, and we can see data from 3 decades, 1990, 2000, 2010. 2020 data isn't yet available, but there is a consistent increase in the amount of carbon dioxide in the atmosphere. And that carbon dioxide is anthropogenic. It's coming from human activities. It's coming from principally the burning of fossil fuels. Humans are tapping into all that fixed carbon that plants created way back 400, 300 million years ago. And by burning that for energy, it is releasing that fixed carbon, converting it back into CO2, introducing that CO2 back into the atmosphere. So this graph is showing the correlation between CO2 concentrations on the y-axis and years on the x-axis. In blue, we see CO2 levels. We see a zigzagging line with an upward slope. The zigs and zags represent annual changes in CO2 associated with summer and winter. So in the summer, plants are pulling more CO2 out of the atmosphere, fixing it. CO2 goes down. In the winter, CO2 goes back up. But the trend line is increasing now today beyond 400 parts per million. The red line shows temperature. There are annual fluctuations in temperatures, and there's hotter years and colder years, but there's a clear upward trend here where year after year in the last few years we've set records for globally high temperatures. So this greenhouse effect is pretty clearly linked to carbon dioxide, and as I stated a moment ago, that CO2 is largely anthropogenic. It's coming from the burning of fixed carbon, mostly from fossil fuels, the coal, the oil, the gas in the ground. There's also a link between living plants and the greenhouse effect, in that massive deforestation is limiting the amount of carbon that can be fixed by living plants and contributing to global increases in CO2. Here's an aerial photo showing a large region of forest that has been clear cut. So all those plants that are gone are now unable to remove carbon dioxide from the atmosphere. For decades, climate scientists have relied on computer models to predict the possible effects of global warming. Today, we don't have to rely on those models. We can look out the window and see some of these effects playing out in real time. Sea level rise, it's happening. Not only does warmer oceans expand and occupy more space, but melting of polar ice contributes to the increase in sea level rise. Life zones will shift. So the simplest way to think about life zones is the Earth has a tropical zone, a temperate zone, and then Arctic zones. And those zones are shifting. So areas that were subtropical are experiencing more tropic-like climates. Temperate areas are starting to experience more subtropical-like climates, etc. So organisms that are adapted to certain temperature conditions are facing warming climates. Weather patterns have long been predicted to become more severe under a warming climate. Pay attention to the news, and 100-year storms happening multi-years in a row is becoming common. One of the sort of nastier scenarios is if ocean currents change. Countries in Europe, for example, enjoy fairly mild climates considering how far north they are, because the current pattern of ocean currents pick up warm tropical water, deposit those off the coast of Europe, and moderate their climate. So if ocean currents shift, whole continents could be experiencing significant changes to the maximum and minimum temperatures in summer and winter. Ocean acidification is something we've talked about previously, and we'll revisit that in the next slide. This slide is dedicated to the idea of life zones, showing the current range of a plant and how, given different warming scenarios, how the acceptable range of temperatures for this plant might be restricted to areas far north of where it currently exists. Here's our figure dedicated to ocean acidification. A recurring theme this semester has been how carbon dioxide in water creates an acidic environment, carbonic acid. Lots of organisms rely on calcium carbonate, CaCO3, to build their skeletons. When there is acidification of oceans, the increase in hydrogen ions ties up the carbonate ions and makes them unavailable for organisms like shellfish and corals to combine those carbonate ions with calcium to create calcium carbonate.